All right, thank you. You are the truly brave. You came to hear me talk twice in one day. That's very patient of you. Anyway, I wanted to talk this afternoon about work going on in Apache Hive 2.0, and I want to kind of walk through some of the technical changes and work going on here in Hive. And Hive really focuses on being three things. We want, obviously it's a SQL engine, we want to be SQL compliant, we want to be fast because nobody ever said they wanted their queries to return slowly, and we want it to scale well, right? We want it to be able to handle petabytes of data. And so I'll focus a little bit on each of those as we walk through this. If I can hit the right button. There we go. Let me start off by acknowledging I'm going to be talking about a lot of things that obviously I didn't build all of this or even most of it. I'm a part of the community, I helped contribute, but many, many other people did. And so I want to acknowledge the Hive community for all the work that it's doing. I also want to acknowledge that I stole some of these slides from some of my colleagues at Hortonworks. And I'm going to talk about a number of Apache projects. And in case I forget to say Apache in front of them, here's my acknowledgement that these are all different parts of Apache. So, as I talked about this morning, and I won't go too much into now, Hive started out as a batch SQL engine, right? It was good at doing doing jobs for very large amounts of data over ETL. Around 2012, it became clear that users wanted to do a lot more than that. They wanted to do more traditional data warehousing, and the Hive community started to shift to deal with that. We don't want to give up the roots that it had. We still want to do that scale well. We still want to be able to handle terabytes or petabytes of data, but we also want it to work for analytics, for reporting, for BI, even for OLAP kind of stuff. So, again, as I talked about some this morning, there were a lot of new feature development went into Hive after 2012. The pace of new features really picked up. But this actually caused some stress in the community. People got a little, there were people who liked Hive as it was, they didn't want it to change, and in their view, all these new features were just adding complexity, breaking their code. Their view was, why are you doing this to me? It doesn't bring any benefit, and you're breaking a tool I already like. So the Hive community came up with a compromise where they would split Hive into a couple versions. So there's Hive 1.0 that's still out there, is still included in, as far as I know, every major version or every major distribution of Hadoop. And the guarantees that the Hive community made around 1.0 is that it would be stable, it would be backwards compatible, and we'd continue to fix bugs in it. Now, that doesn't mean that you can't add new features here. You can if you're a Hive developer and you want to add to it. That's completely fine. But you can't break the system. You can't do things that aren't backward compatible. On the 2 line, instead, this is where we're going to keep pouring new features. And here we said we would be backward compatible whenever possible, but sometimes in interest of getting new features in or maybe fixing strange ways that Hive did things in the past, we would not necessarily guarantee that we'd be 100% backward compatible. And I'll talk here at the very end, I'll talk about some of the ways we did break that, just so you know what's out there. I keep hitting that wrong. There we go. So Hive 2, the first release, came out in February of this year, so a while ago now. And you can see there that over 1,000 JIRAs were resolved as part of that. JIRA is our bug tracking system. So that's a lot of bug fixes, a lot of new features, a lot of new code. That gives you some idea of the amount when I'm talking about things being, the pouring new features in, maybe lowering stability a little bit for people who are already happy with the way Hive was, where some of that's coming from. And then 2.1 was released here in June of 2016. Not quite as many JIRAs resolved, but still lots and lots of changes. And I looked the other day at the kind of tip of master, and we're back. We haven't done a release since June. We're back in about the 1,000 range for a number of JIRAs closed that will eventually be released. So you can see that there's just a lot of development happening in the community. I don't have time to, or enough voice left to go through all the new features that are happening in Hive. So I want to just kind of look at a few of them. I want to talk about adding procedural SQL to Hive, the new LLAP work that I talked a little bit about this morning, some improvements to Hive on Spark, our work on the cost-based optimizer, and then toward the end, I'll touch on some of what's going on in the Hive community right now that's being put into the 2.0 line that I think is interesting and exciting. So to start off with, let's talk about procedural SQL. If you're familiar with Oracle's PL SQL or Teradata's stored procedure language, these are examples of taking SQL and adding loops, cursors, branches, if statements, for statements, so that you can write complete stored procedures in or small programs in your SQL code, right, without having to jump in and out of SQL. This is not part of the SQL standard, but it's very commonly used in a number of database packages. So this was added to Hive in 2.0. This was a contribution from a member of the community. Actually, he wasn't a member of the community yet. He was somebody from the outside who wrote this, and we found it and said, hey, how'd you like to join us and contribute this code, because it looks pretty cool. So that's there in 2.0. Now, the one thing is it's not yet completely integrated into Hive, since it was originally written from the outside. It's a separate binary right now, where you run the binary with and give it your HPL SQL script, and then it connects to Hive via the JDBC driver and submits it. Obviously, what we'd really like is for this to be inside Hive itself, so you could directly connect to the JDBC driver and then submit your HPL SQL. But still, this gives you a way to start to write stored procedures in Hive that you can share between different users. One of the big drives in Hive over the last 3-4 years has been to speed up performance, right? And LLAP really kind of completes that drive to being able to answer queries in sub-second times. And it does stand for live long and process, taken from Star Trek with the Vulcan symbol and all. This is why you never ever let your engineers name your projects, because this is what you get when that happens. But let me give just a little motivation for where this came from and why we did this and what we're thinking and kind of where we're trying to make it go. So Hive started out as a Hadoop application. All Hadoop applications, you submit a job, Hadoop finds some containers for you, slots, some tasks that you can run, you spin up JVMs, and then you get going. All that takes time, right? And no matter how hard you work, you really can't cut that below, say, 5-10 seconds, because you're just up against the amount of time it takes you submit an RPC, Yarn finds a place to put your application master, so that JVM spins up. Now your process has to go talk to that application master and say, I want this many nodes, and then it has to go to Yarn and say, okay, I need these many resources. And there's just a lot of back and forth and a lot of spinning up JVMs. You can't get rid of that time. Our goal was to push Hive to the point where it could answer quick queries quickly. Right? If you've got a human sitting at the terminal, you don't want every query to have a 5 to 10 second pause just when it spins up, especially when it's over a short amount of data. And so we knew we needed a way to solve that. We'd already done lots and lots of work to speed up the processing of Hive once it had started processing, but we needed to speed up that startup time. So we decided we wanted to work on using persistent daemons for this. Now, we didn't want to go full-on MPP, which is the way a lot of these systems are built, because those systems work really well when the data fits in them, and then they scale to a point, and then they have a hard time scaling past that. And we wanted Hive to keep working in the Hadoop world where it could scale very well for very large data sets. And so we came up with this hybrid approach where When it's appropriate, we can act like an MPP system with LLAP, and when it's not appropriate, we can act like a more traditional Hadoop application where we're spinning up containers or spinning up tasks and running our job. Okay, so what did we put in these persistent containers? How do they run? So if you want to use LLAP, you start up Hive, you tell it how many nodes you want for this. You don't need to put one on every cluster, or sorry, every node in your cluster. You can, in fact, in general, we would not expect you to do that because we don't expect other applications running on that same node as an LLAP daemon, because the LLAP daemon is basically going to want to take all the memory it can. So you dedicate some amount of your cluster to this, and then these daemons can cache the hot data sets and push, and you can do some processing in them as well, and I'll talk a little bit more about that in a moment. So let me talk about this caching. The caching in LLAP is aware not just of tables, but partitions and even columns inside partitions. So it can, as you query the data, it can figure out which pieces of that data are hot, meaning which ones lots of people are hitting, and it can start to cache those. And in fact, it's not, in many of these types of systems, a particular part of the data gets mapped to a particular node, and everybody who needs that data goes to that node. We don't constrain a cache to an instance of caching data to only one point in the cluster. So say that you have very hot data, maybe yesterday's results just came in, and you have a whole set of jobs that jump on top of that and start reading it really quickly. Each node in the LLAP set is only going to be able to answer so many queries, right? We don't want to flood it. We have to slow that down. But we also don't want all the other queries that need that data to wait until there's a slot on that one node while the other nodes are doing nothing, because that's the one data set, the one bit of data everybody wants, right? So we actually, when we start to see that, when a node that contains the data is filling up, we make another instance of that data in another node and tell the ones that are backing up behind it to go there. So depending on how hot your data is, it may be cached actually multiple places in the LLAP cluster so that we can service all those requests. An interesting thing is that, originally we thought much of the savings from LLAP would come with, we don't have to spin up tasks because they're already running, and we don't have to, we can keep the hot data cached, and that does buy you quite a lot. But we also found that one thing that buys you quite a bit is Java's just-in-time compiler doesn't have to get started every time. Every time you start a JVM, it doesn't know anything about your code. It has to go through a few 100,000 iterations before the JIT kicks in and optimizes your code. And we've found with Hive's operators, whether you're running with or without the JIT, you get a very significant change in performance. And so by running these daemons consistently, not switching not taking up and down the JVMs all the time, we are able to benefit from that JIT on the first record through on your query. So even if your query is only going to end up touching 100,000 records, you're still going to benefit from that. So let me talk a little bit about how tasks actually run. I've talked about LLAP as a cache, but it is more than a cache. It can actually run some of the tasks. And here you see 3 examples of ways you could run code in Hive today. So as I said, you're not forced to use LLAP. If that doesn't make sense, say you're going to do a query over the last year's worth of data. You want to do, it's the end of the year, you need to do a full year's report on how much you sold on your website or whatever this year. A year's worth of data isn't going to fit in your cache. And you probably aren't going to run query after query over that, so it doesn't make sense to cache it anyway. So you don't want to run that through LLAP because you don't want it to end up flushing all the data you actually are reading all the time out of your cache. In that case, you would run it here in the leftmost panel. Let's see do I have a laser pointer? Maybe. Yep. Over here, in the TES-only mode. And that way, you can still scale, right? If this is a year-over-year query, it's going to touch maybe 10 terabytes, 20, 30 terabytes of data. It's fine. You can scale out, get lots and lots of tasks. In this case over here, you see an operation that maybe can run all in LLAP. Let's say you're just doing a query over the last hour's data. So maybe that's only 500 gigabytes, not that much. Something you can easily run inside these, inside the daemons of LLAP, and there's no need for it to ever go out to TES to finish the processing. It can do this work itself inside, maybe shuffle between the daemons as it needs to, and give you an answer all without overrunning the capacity of those daemons. This gives you a way to answer some of these queries very, very quickly. And finally, you can envision things that might work in a mixed mode, where you're reading data out of the cache, but you're going to do some things to it that wouldn't fit well in LLAP. Like maybe you're going to do a very large join that's going to produce a big explosion in the number of records. And you expect the output of that join to swamp what LLAP could hold. Then you're going to pick this mixed mode here. But the point is, you can push all this, when it makes sense, processing can be pushed down into these daemons rather than run in separate tasks that have to be spun up, and you have to require shuffling data around the cluster and all that stuff. So how's this working out? How's the performance? I want to show you a couple performance graphs. I showed this one briefly today in the keynote. This is Hive 1 with TES versus Hive 2 with LLAP. The bigger green bars are Hive 1, obviously. The small, hard-to-see bars are Hive 2. And so you see there we've got some very significant speed up across some of these queries. Now, just truth in advertising, this is a little bit of cherry picking. Not every query is faster with LLAP than without. As I said, there are queries it doesn't make sense to run in it. Those would obviously be slower. LLAP is also not 100% done, baked, and ready. I would consider Hive 2 and 2.1 both to be in beta state, and so there are some areas that probably still need some work, where Hive might work better without LLAP than with it. So this graph gives the impression, this is a marketing graph. It gives the impression it's always better. It's not always better. It's almost always better. But I want to show one other graph here of some recent performance numbers we did. This is a comparison against a more pure MPP system, which is Apache Impala. And this is a benchmark we ran recently. And again, this is a TPC-DS data set, which is a set of decision support queries that we feel are common to what users would tend to use Hive for. And I believe both these tests were run over a 10 terabyte data set. So big enough that it couldn't completely fit in memory, which obviously we chose intentionally. Now, in this test, we ran it against Impala. We tried to pick what was optimal for each side, given the same, we gave them the same hardware, but on the Hive side, we used our HTTP 2.5. We encoded the data, or we stored the data in ORC, compressed it with zlib, because we know that's the way Hive does fastest. On the Impala side, we used the latest CDH. We stored it in Parquet, because that's what Impala works well with, and compressed it using Snappy, because our understanding is that that's the fastest way to use Impala. So we tried to be fair and run it as fast in each way. And you see, it kind of came out a wash. About half these queries, Hive is faster. About half these queries, Impala is faster. And there's no obvious place where one's completely skunking the other. They're both doing reasonably well, and there's kind of balance there. So why am I showing this if it's not showing how much better we are? Because what I want to show is, I think we're starting to reach our goal of being able to act like an MPP system when it makes sense. Impala is a pure MPP system. That's its sweet spot. We're trying to be able to operate in that space as well as the very large data space. And so this is, for us, a very encouraging outcome that we're starting to be able to do that when it makes sense to act like that, we can do that. So what's still going on? I already said once that LLAP wasn't fully baked. There was work to do. What is left to do? Right now it's read-only. we're still working on having a write path. Now, that doesn't mean you can't write to tables when you're using LLAP. You certainly can, but you have to write to them in more old style without using LLAP. There's a JIRA right now that's being worked on there. That's actually an umbrella of JIRA for a number of different things that are being done to add a write path. The write path is particularly important for us in the cloud, where being able to have the data cached in LLAP gives you even more benefit, because if you have to go read the data out of S3 or some blob store, that's a lot bigger penalty than just having to read it out of HDFS. As I think I've said a little bit, Hive now supports transactions like update, delete, insert. That integration with ACID is not yet done in LLAP. Again, you can read ACID tables, but you can't do those updates and such through there. That's also being worked on as part of the above work on the write path. I showed you those 3 different query modes, the kind of TES only, mixed mode, and LLAP only. Ideally, Hive itself would be able to figure out what mode to use, right? It should be able to look at your query, do some cost analysis on it, and make some decisions about what mode to use. Today, it doesn't do that. Today, it depends on you telling it, do this or do that. That's obviously something we'd like the cost-based optimizer to decide for us, and in the future, I imagine it will. We started out integrating LLAP just with ORC files, with ORC, which is a columnar storage format that we use. We're working on adding support for other storage formats there. I believe text is being worked on right now, and I think they're working on figuring out what the best way to integrate Parquet is with this, so it could work there as well. And then today, LLAP requires that you use TES as an engine. So Hive can run on 3 different engines underneath. It can use TES, MapReduce, or Spark, any of those 3, to actually execute its queries in the Hadoop system. LLAP is very tightly integrated with TES, and so I actually kind of suspect this part won't change. I don't think it will end up supporting more than 1 engine there, because you'd have to rewrite quite a bit of LLAP to generalize that and make it work with a different engine. All right, so having talked about that for quite a bit, let me talk about some of the other things that are going on in Hive in 2.0. Another big area of investment in the Hive community has been making Hive work on Spark. So as I just said, you could have these different engines. Spark is one of the options. There was a lot of work that went in Hive 2.0 to improve how Hive worked on Spark. This included being able to do dynamic partition pruning, which Hive with TES could already do, but Spark didn't support yet. This is where you realize sometimes you can't figure out what partitions you need to read until after you start to evaluate the query. Basically, there may be something in the join clause that ends up making it so you don't have to read a bunch of the partitions, but you can't realize that when you're compiling the query. You have to do it once you've started to run the query. And so that was added to Hive on Spark. In Hive, by default, if you do a self-join, select something from A, join A, where it's both the same table, by default, it will load that table twice, which is obviously very inefficient. Spark gives you a very nice way around that, because you can load the table into an RDD once and then read from it both times. So that was added for self-joins, unions, and CTEs is the with clauses, where you're going to load you're going to run basically part of a select query against something, and you can leave that in an RDD. There were other improvements to support map join with the new vectorized operators. These are operators that are much, much more efficient than the old style 1 record at a time operators. It was made so that you could do an order by in parallel. By default in Hive, if you have an order by, that has to be run serially, kind of at the end of your query. Usually that works out okay, because usually by the time you're doing an order by, you don't have very many results left, but sometimes that's not true, and so support was added to do that in parallel. And then support was added to do a better job of warming containers for Spark. There was somehow the way Hive on Spark worked at first, there was a bug in the interaction between Hive and Spark where it would often end up not using all the containers it should have, and that was fixed and made much more efficient. And then support was added here for Spark 1.5. I'll talk later about updating that, since obviously Spark has moved a ways past 1.5 now. Okay, let me talk a little bit about our cost-based optimizer too, and I'll back up a little bit and just talk about what that means for just a second. There's a couple kinds of optimizers in databases. There's rule-based optimizers that that make optimizations you always know you want to do, and that you can figure out by looking at the query when you start, right? For example, if you have a query that has a join in it and a where clause, and that where clause only applies to one side of the join, only one table in the join, it's always more efficient to push that where clause up in front of the join and evaluate it before you evaluate the join, right? That's an example of a rule-based optimization. But there are lots and lots of optimizations that you cannot figure out by looking at the query when you compile it. And the easiest example of seeing that is if you've got a query that has 2 joins in it. Maybe a fact table with multiple dimension tables. The order you choose to do those joins in can have make orders of magnitude difference in the performance of that query. But there's no way that just looking at the SQL you can tell, oh, I know I ought to join A with B before I join B with C. That's something you can only figure out by looking at the data that you're going to run it on and making a guess at which one will be faster. That's what a cost-based optimizer does. It uses statistics to make estimates about what's the least expensive way to perform a query. Now, Hive uses a project called Apache Calcite to build its cost-based optimizer. We haven't yet finished migrating our rule-based optimizer into that, but we're working on it to the point where eventually Calcite will be our only optimizer. For now, we have a few of the rules left in Hive. But in 2.0, we actually started turning on the cost-based optimizer by default. This is not the first version with it, but it was the first version where we felt it worked well enough to actually use it. In the earlier versions, it was kind of just getting started, and the results it gave were only sometimes the best answer. We've focused the CBO work on improving these TPC-DS type queries because we believe that's what a lot of people are trying to use Hive for. I mean, not obviously the TPC-DS queries themselves, but queries like that in their work. So that's what we're using as to guide our development there. And we've spent a lot of time focusing on improving our stats collection and estimation, because a cost-based optimizer is only as good as the statistics you give it, right? No matter how good your optimizer is, how smart your algorithms are, if you're feeding in garbage statistics, you'll get out wrong results. So we've spent a lot of time working on that. Okay, there's many, many more things here that I won't have time to cover, but I encourage you to look through some of these. The slides I hear will be posted later, so it'll give you a chance to go through and look at this. There's just a lot of extra goodness that has been added here. I want to finish up with just some hints at what's being worked on now in Hive 2. What are people focusing on? There's a lot of exciting areas, actually. There's a number of things going on. LLAP is being hardened for GA, so one of the big ones. There's a lot of work going on in the transaction/ACID space. So this has been in Hive for a while now, but one of the downsides of using transactional tables in Hive initially was the way the data was laid out. They were significantly slower to read often than regular tables. There was a big performance penalty for it. So we did some work last summer to rework how those files were laid out. The way Hive actually stores updates and deletes, since of course you can't make changes in HDFS, is it writes them on the side in a Delta file, and then at some point in the background later merges the Delta files into the main file. But in the meantime, a reader is responsible for merging that Delta file with the base on the fly. The way we had originally done that, the readers weren't as fast as we wanted them to be. We did some work to change the layout of those Delta files and very significantly speed up the readers so that you don't see this big performance penalty for using ACID anymore. We're also adding the merge keyword in for ACID. So merge is a SQL command that basically amounts to upsert. It gives you a way to load a bunch of records into a table, and then at some time in a single pass, you can take all the records in the table and add them to another one. And basically what merge does is it says, okay, if this record already exists in the base table that I'm merging into, then it becomes an update. I'll take whatever changed values are in this new table, and I'll update the base table. If instead that record doesn't exist in the base table, then it becomes an insert. So that's often called an upsert. This is very commonly used in data warehousing, where you're pulling in data from, say, your transactional stores. You're streaming it in very quickly. And Hive and HDFS, of course, can stream data in very quickly. So this is easy. You write it quickly into a table, and then maybe every 5 minutes you run this merge command so that in a single pass you can merge that data in and have the changes. We're adding support for transactional inserts into non-ACID tables, so tables that aren't transactional, we can still make the inserts themselves transactional. We've vastly improved how easy it is to read explain. So if you want to explain your query, it used to be almost impossible to figure out what the results of that statement meant. Now that's not actually true. Materialized views have been added, so you can create materialized views in Hive. We're integrating Hive with a project called Druid, which does, which is kind of a system that's very good at storing aggregates of data on the fly, and we can use Druid as a way to do slice and dice on a number of queries, so supporting cubing type operations. So we're doing that integration in Hive. We're continuing to progress towards supporting full SQL 2011, adding things like intercept and accept, extending our subquery support, and adding support for non-equa joins, because we just see people trying to do more and more of these sorts of things. And then the Hive on Spark group has added Spark 2.0 support, since that's kind of where Spark's at these days. All right, so I promised toward the end I would talk about what we actually broke. What moving from Hive 1 to Hive 2, what do you expect to not work anymore? Some of it is we just dropped support for older stuff, so we don't support Java 6 anymore. We now require Java 7. There have already been some discussions about when we might start requiring Java 8 and move off of 7, but we haven't done that yet. I don't know if too many people are using 6 still in the field, but probably somewhere someone is. We also don't support Hadoop 1 anymore. You have to use Hadoop 2. I don't think that's going to cause too many people trouble. We've deprecated MapReduce as an engine. So we don't, it still works, we still support it, but we're just giving notice that at some point in the future we'll drop it out. We really recommend Tez or Spark instead. They've come along to the point where they're much more efficient, and we're not aware of issues that work in MapReduce that don't work in Tez or Spark. So at some point in the future we'll drop it off. Something that catches people by surprise when they install Hive 2 is we actually change some of the default configurations. For example, we actually turn security on by default now instead of having it turned off by default. We enforce some things like bucketing if the table says it's bucketed that we didn't enforce before. Some things like that, where if you're doing an upgrade and you're not expecting this, you might see some behavior changes. And then finally, at some point in the future, we plan to remove the command line interface for Hive and just use Hive Server 2, which is a ODBC JDBC connection. Now, there is still a command line tool called Beeline that connects to Hive through JDBC, so there still will be a command line option if you want to script your stuff. And in fact, hopefully we will have it so that Beeline will be 100% backward compatible with the CLI, so that the transition is seamless in terms of your actual scripts. But the reason for this is security. When you run Hive in the command line, all the query planning is done actually in your process. That means that that process has to be able to have access to HDFS. That makes it impossible to lock down certain security things, right? You can't, if the user can touch HDFS, we can't do things like enforce columnar security. We can't enforce, if the data is encrypted and we have to decrypt it, we have to put the keys into your user space. We don't want to be doing those sorts of things, right? So it's just much easier to have that block at the server where we can handle security, we can handle encryption, all that, and still hand you the data and know that we're doing it securely. All right. That's what I had. Do we have any questions? And I think we have a mic for the question. We have a question over here.
I'm afraid to ask a strange question. How do you compute, how are you going to compute statistics for the cost-based optimizer?
So we compute statistics. Right now what we track are per partition, we track things like min and max values for each column. We track number of distinct values and number of non-null values. We would like in the future to move into storing some histograms and such so we get some kind of idea of the layout. We're not doing that today, so that's not there yet. Obviously, when we can do that, we'll vastly improve our the accuracy of our optimizations, especially for joins and group bys. And like right now today, we just have to make a guess about how selective a filter is, right? Once you have a histogram, you can figure that out. Now, we do also at the file level keep some statistics. In addition to those ones I was talking about, we keep some Bloom filters that we can use for things like pushing predicates down into the scan and that sort of stuff. But that the optimizer isn't using yet. Other questions? Oh, okay. Okay, so do we have a date on where we're going 2.0? So I can't give you an exact date, I can give you a goal. So obviously it'll be somewhat up to the Hive community to decide when to release this. Hortonworks plans to release in Q1 of next year, January, February, March, somewhere in there, and we would like to have a GA version of Hive 2.0 at that point. Just be aware it's a goal, not a promise yet at this point, but that's the plan. Other questions? All right, excellent. Thank you very much.